Welcome everyone. In today's lecture, we are essentially going to continue with the 3D stress analysis that we started in the last lecture. Okay. So what are we going to learn in this lecture? So we're going to do two things. One is we will learn how to compute the invariants of the stress matrix. I briefly alluded to the stress invariance in the previous lecture. In this class, we'll kind of look at it more carefully. And then we will also learn how to calculate the maximum shear stress and determine the plane of the maximum shear stress. So if you recall, in the last class, we looked at principal stresses and how to find the principal planes. So here we will look at how to find the maximum shear stress and the plane of the maximum shear stress for 3D stress states. Okay. So just to kind of recap what we did in the last class. So if you are given the stress at a point in the XYZ coordinate system. Okay, so again, we always talk about the stress at a specific point. Okay, and if you are given the stress matrix at that particular point, then we find the principal stresses at that particular point by essentially taking this determinant that I have written here and equate that to 0. So essentially, you take the stress matrix sigma minus, sorry, let me just erase it. So you take the stress matrix sigma minus sigma p times I. Okay. So this is both matrices, and the determinant of that should be equal to 0. That is what is written here. Okay. So that's what we do. Okay. So if you take the determinant of this particular matrix, what you will find is that you will end up with a cubic equation in sigma p. So if you think about the first term in the determinant, it will be sigma x minus sigma p times sigma y minus sigma p minus sigma z minus sigma p. Okay, so essentially you will get a cubic term in sigma p just because of that. Okay, and of course it will have terms that are quadratic in sigma p, terms that are linear in sigma p, and also you will have a constant. So that is what this equation refers to. Okay, that is okay. But here I have made a specific notation. So I have said it's sigma p cube minus I1 times sigma p square plus I2 times sigma p minus I3 equal to 0. Okay. Now, if you look at this matrix, what you will automatically realize is that this I1, I2, I3, and so on will be composed of sigma x, sigma y, sigma z, and tau xy, tau xz, and tau xy, and tau yz. Okay. So essentially, this I1, I2, and I3 has to be composed of some combination of this normal stresses sigma x, sigma y, and sigma z, and the shear stresses tau xy, tau xz, and tau yz. Okay. So why did I write it as I1, I2, and I3 instead of actually writing it explicitly in terms of sigma x, sigma y, and so on? Okay. The reason is that these coefficients of sigma p square, sigma p, and the constant term are unique in the sense that they are defined and they're always constant irrespective of what coordinate system the stress matrix is given. Okay, so this is why they are called the invariants I1, I2, and I3. Okay, so I just want you to focus here. If you are given the stress at a point in the XYZ coordinate system and you calculate this I1, I2, and I3, okay, you will get some values. Now, if I give the stress at the exact same point in a different coordinate system, okay, x prime, y prime, and z prime, and then you calculate the I1, I2, and I3 for that particular coordinate system, they will be identical to the one that you calculated before. Okay, so that is why they are called invariants, and we will kind of reason out why that should be the case in the next slide. Okay. For the moment, just assume that this I1, I2, and I3 are constants, and these are given by these particular equations. Okay. Okay. So I1 is nothing but the sum of the normal stresses sigma x, sigma y, and sigma z. I2 is essentially the product of the stresses sigma x, sigma y, sigma z, and sigma z, sigma x. And then you have a negative term that is composed of tau xy square, tau yz square, and tau xz square. And I3 similarly is a cubic term in sigma. Okay, so again, I don't want to kind of read every term there. You can see it yourself. Okay, so this I1, I2, and I3 are the invariants. Okay, and why are these three invariants? Okay, and the reason is, think of a situation that I was just describing below. Okay, you have a body and you have a point inside that body. Okay, now you can define three planes that go through this point. Say this is the x plane, and that is the y plane, and a plane that is perpendicular to x and y, say that is the z plane. Okay? So essentially, when you give the stress matrix at this point in the xyz coordinate system, what is essentially given is the stresses on the x plane, y plane, and z plane, both the normal stress on those planes and the shear stress on those planes. That is the stress matrix sigma, okay, in the xyz coordinate system. Okay. Now you can consider the exact same point P, okay, but now I can define three different planes, x prime, y prime, and z prime. Again, x prime, y prime, z prime, all of them are perpendicular to each other. Okay. Now I will get a different stress matrix at the exact same point, okay, in the x prime, y prime, z prime coordinate system. So I want you to remember that the body is the same, the point you are considering is the same, the loading is the same, everything is the same. The only thing that we are doing differently is that we are looking at the stresses on three different planes passing through the same point. And those three different planes are the x prime, y prime, and z prime. Okay? And if you look at the normal stresses and the shear stresses in those planes, x prime, y prime, z prime, they will be different from the normal and shear stresses in the x, y, z prime. Okay? So that's why the stress matrix in the x, y, z coordinate system and the x prime, z prime, y prime, z prime coordinate system at the exact same point will be different. Okay? But now, if you think about the principal stresses, what does the principal stresses mean? So these are the stresses, okay, on planes that pass through the point P where the shear stresses are 0. Okay? So these principal planes and principal stresses should not change irrespective of whether the information that you initially provided was in the xyz coordinate system or the x prime, y prime, z prime coordinate system, because these are in some sense real physical planes on which the stress, the shear stress is 0. Okay? And those planes and the normal stresses on those planes, which are essentially the principal stresses, they should not change whether you were given the information in the xyz coordinate system or the x prime, y prime, z prime coordinate system, or some x double prime, y double prime, z double prime coordinate system. Okay? Irrespective of what coordinate system you are given the stress matrix in, the principal planes and the principal stresses will not change. So which means that this particular equation that we get, right, should be the same, because sigma 1, sigma 2, and sigma 3, or sigma p1, sigma p2, and sigma p3, they have to be the same, which means that the coefficients I1, I2, and I3 have to be the same. But these coefficients I1, I2, and I3 are essentially these in terms of sigma x, sigma y, and sigma c. Okay? So if I1 is sigma x plus sigma y plus sigma z, it has to be equal to sigma x prime plus sigma y prime plus sigma z prime. It should be equal to sigma x double prime plus sigma y double prime plus sigma z double prime. Okay? So that is the reason why these particular terms are called invariants. Okay? So irrespective of what coordinate system in which the stress matrix is given to you at a particular point, if you compute these quantities, sigma x plus sigma y plus sigma z, that should be always the same. The sum of the normal stresses at the point has to be always the same. Okay? So that is the reason why you call these things invariants. Okay? And we will look at examples in our homework where you will actually compute this invariance in different coordinate system and find out that actually they are the same. Okay? So that is what we call that we need to know about the invariance or stress invariance. Okay? Now let's go a little bit further, okay, and think about this, what is called as a principal coordinate system. Okay? So when we started this 3D stress analysis, we looked essentially at two different coordinate systems, right? Something like, say, this is, x, y, and z. Okay? And then we looked at a different coordinate system, say, x prime, y prime, and z prime. Okay? And we learned how to transform stresses from the xyz coordinate system to the x prime, y prime, z prime coordinate system. Okay? Now, there is something called a principal coordinate system. What is this principal coordinate system? So if you think about the notion of principal stresses and principal directions, if you are given the stresses in the xyz coordinate system, okay, now you can think of this as the stress cube. Okay, that is the x, that is the y direction, and that is the z direction. Okay, and you know or given, or you know or either given the stresses on this planes or the faces of this cube. Okay, now if you take this same point, now you rotate the cube in such a way that the cube's faces are along the principal direction. So it's O1 cap, O2 cap, and O3 cap. Okay, then in that particular case, these faces here, they will have tau to be equal to 0. They will not have any shear stress. Okay, that is what we are doing. So essentially we are looking at 3 different planes passing to the exact same point, but those planes are special in the sense that they don't have any shear stresses. Okay, and the normal to these stresses or normal to these planes are these O1, O2, and O3. Okay, so in some sense, this O1, O2, and O3 define a new coordinate system. Okay, and that coordinate system is what is called as a principal coordinate system. Okay, so what does this actually mean, right? So when you find O1 or O2 and O3, or OP1, OP2, and OP3, what are we doing is that we are getting this direction cosines, LP1, MP1, and NP1. And this is what we learned in the last class, how to actually get this LP1, MP1, NP1. Okay, so essentially this O1 cap, which is a unit vector along the principal stress direction number 1, is nothing but your LP1 times I, which is a unit vector along X, plus MP1 times J and NP1 times K. Okay, so this O1, O2, O3, or O1 cap, O2 cap, O3 cap, essentially, they themselves define a coordinate system, and that is called a principal coordinate system. Okay, so what is special about this principal coordinate system is that when the coordinate system is the principal coordinate system, the planes that are perpendicular to those unit vectors basically have 0 shear stress. Okay, so what does it actually mean is that if you go back to these equations here, let me just erase some of this. Okay, so if you look at these equations here, the first term has normal stresses, but the second term has only shear stresses. Okay, so if you're operating in the principal coordinate system, the shear stresses will vanish. And here, if you look at the third invariant, both these terms will vanish. Okay, so your I1, I2, and I3 become actually much, much simpler. So if you look at what is I1, I2, and I3 in the principal coordinate system, it is going to be much simpler. Just sigma 1 plus sigma 2 plus sigma 3, sigma 1, sigma 2, sigma 2, sigma 3 plus sigma 3, sigma 1, and I3 is just one term, sigma 1, sigma 2, sigma 3. Okay, so essentially, you can actually verify whether the I1, I2, and I3 that you get in different coordinate system is same as the I1, I2, I3 you get in the principal coordinate system. Okay, there's also another thing, that's a subtle point that I want to make here, is that we always looked at how we can transform stresses from the x, y, z coordinate system in which you are given the stress matrix to an x prime, y prime, z prime coordinate system. Okay, what you can also think of is actually transforming your stresses from the x, y, z coordinate system to the principal coordinate system. Okay, and how do you do that transformation? So typically, you essentially have sigma in the x prime, y prime, z prime coordinate system is nothing but the transformation matrix T times sigma in the x, y, z coordinate system times T transpose. Okay, so you can define the transformation matrix T for the principal coordinate system, which I define as TP, as nothing but O1 cap transpose, O2 cap transpose, O3 cap transpose. So O1, O2, O3 are essentially the principal directions. So essentially, your stress transformation matrix for transforming from the XYZ coordinate system to the principal coordinate system is given by this matrix here. Okay? So what I mean by that is that sigma in the principal coordinate system will be this TP times sigma XYZ times TP transpose. Okay? And if you want to write it more explicitly, sigma 1, sigma 2, sigma 3, because remember, in the principal coordinate system, the shear stresses are 0. So all these off-diagonal terms are 0. Okay? And that is going to be equal to Tp times sigma in the xyz coordinate time system times Tp transpose. Okay? Now, there's also a couple of other things that you probably want to note here, is that once you know the principal stresses sigma 1, sigma 2, and sigma 3, you can find that the tau max is sigma 1 minus sigma 3 divided by 2. Okay? Again, I want to emphasize that once you find the principal stresses, you always order them in the way that sigma 1 is greater than or equal to sigma 2 is greater than or equal to sigma 3. Okay, so you always order them in such a way that sigma 1 is greater than or equal to sigma 2 is greater than or equal to sigma 3. Okay, and this is including the sign. Okay, so for example, if you have three principal stresses, say 5 and 10 and minus 20, then your sigma 1 will be 10, sigma 2 will be 5, and sigma 3 will be minus 20. Okay, it could be minus 20 MPa, minus 20 gigapascal, it doesn't matter. Okay, so that is how you order them. Okay, so sigma 1, sigma 2, sigma 3 is usually the notation that we use for principal stresses. Sometimes it's also mentioned as sigma P1, sigma P2, and sigma P3. So I want you to be comfortable with all the notations. Okay, now this is how you find the maximum shear stress from the principal stresses. Okay, now how do you find the normal to the plane on which this maximum shear stress occurs? Okay, there's a simple way to do that. The simple way to do that is essentially the average of O1 cap and O2 cap. Okay, so O1 cap plus O3 cap divided by 2. Okay, what do I mean by that is that O1 cap is the direction of the maximum principal stress. O3 cap is the direction of the minimum principal stress. Okay, so these two directions are orthogonal to each other. Okay, now you can define a plane in which the two orthogonal vectors are O1 cap and O3 cap. If you consider that plane and you draw a line that is at 45 degrees to both O1 cap and O3 cap, like the way I have drawn here, that is OS cap, which is the normal to the plane on which the maximum shear stress occurs. Okay, so if you kind of want to look at it more explicitly, if this is your, let me just draw the principal stress plane. Say these are the principal stress planes. Okay, so this is O1 cap, and say let me call this as O3 cap. Okay, so if you look at a plane that is at 45 degrees to both these planes, so let me just use a different color here, a plane that is at 45 degrees to both these planes, that is the tau max plane. Okay, so that is something that you must keep in mind. Okay, so again, this O1, O2, and O3, these are normals to the principal planes, and similarly OS hat or OS cap is the normal to the plane on which maximum shear stress occurs. So essentially, if you bisect this O1 and O3, that is your OS cap. Okay, so I hope that this kind of makes the whole picture clear on how we do stress transformations, how we get principal stresses, how we go from the given coordinate system to the principal coordinate system, and how you use the principal coordinate system to find out where the maximum shear stress or the plane on which the maximum shear stress occurs. Okay, I'll see you in the next class. Thank you.